Hi, and welcome to our next session here in our chapter on classification. So this is a somewhat longer session on discriminant analysis. Well, at least it has a double-digit slide number. I hope the video is not going to become too long. So there's quite a few simple worked out examples here, which I hope you'll enjoy and which will make the methodology a bit clearer. I hope I'm not going to spend, I don't know, a super crazy amount of minutes while explaining these. So here, as the title says, we'll look at two simple classifiers from the family of discriminant analysis techniques. So LDA, linear discriminant analysis, and QDA, quadratic discriminant analysis. And the reason they are called like that is because linear discriminant analysis will produce a linear classifier and quadratic discriminant analysis will create a classifier with quadratic decision boundaries. They are both also based on the normal distribution. They are both so-called generative models. So we are modeling the conditional density of feature vectors given that we are in a specific class. Discussed this a little bit before. We'll see this here now in detail in action. Yeah, and I'll also, of course, explain how the parameters are estimated of these two models, which is a little bit different than our, because they are basically just using these distributional assumptions. So you'll see that we don't really need empirical risk minimization to estimate parameters. We don't really have to do a lot of optimization. We're just estimating parameters. So mean vectors and covariance matrices of Gaussians. And we know how to do that, and we don't really have to do a lot of optimization for that. So as we have covered before, we want to now use this generative approach to model our posterior probability of being in class K, given that we are observing a certain feature vector x. So far so simple and so intuitive. We've said that for a generative model, we can now use Bayes' theorem to turn things around and then apply the law of total probability here in the denominator to get our hands on an expression which just consists of two different terms. So one are these pi k's here, and these pi k's are simply the prior distributions of the classes. So the class sizes, so to speak, the probability without observing anything to be in class 1, 2, or 3. And more importantly, the second term would be this guy here, or these guys, so to speak. So the conditional distribution of a feature vector x conditioned on the fact that we are in a certain class K. So if we have a concrete form for this conditional density, given that we are in class K, we can now work with this model and we can compute these posterior probabilities and we can use them for prediction. So the only thing we now have to do is to assume, or at least we can do that. So let's assume some distributional form for this conditional probability, given that we are in class K. And what we'll assume here is that our data is constructed in each class, so not globally, but conditionally that we are in a certain class by a multivariate Gaussian distribution. So you can see this here down below. I have two classes, a blue one and an orange one. And the data is, it's quite likely that the data is actually sampled per class from a Gaussian. And you can see something in addition here. So it doesn't only seem to be normally distributed, at least roughly. It also looks like the covariance structure of both classes seems to be the same. And linear discriminant analysis makes, in addition to this multivariate, makes another assumption in addition to that conditioned on the fact that we're in a certain class, things are Gaussian. It also assumes that the covariance structure of all of the classes, it's a multi-class classifier, so we can only model two classes, but potentially multiple. The covariance structure in all classes, the covariance matrix sigma k, these guys are all the same. So that doesn't necessarily have to be true for data situations, but that's the assumption that the model makes, that LDA makes to simplify things. Yeah. Okay, so what can we now do with this? I guess maybe we could go through a univariate example. We can study how this feels for a very simple situation. So I've constructed something here, super naive toy example, not very realistic, but yeah, maybe easy to deal with, easy to reason about. So this would be a situation where we would classify a person either as male or female based on their height. Okay, so yeah, I'll give you a certain height in centimeters, and the idea is now to compute the probability whether the person is male or female, because I guess on average males are have somewhat larger body sizes. So I don't want to talk too much about estimating parameters here. We'll do this a little bit later in a few minutes. So here I will do the computations in the true data generating process. I'll do the computations with reference to the underlying distributions, but the model for LDA will perform similar computations if you just go from your true probability distribution to estimated ones based on parameters. But like I said, we'll discuss that in a few minutes. So let's just assume we now know everything, and we know joint and the conditional distributions, and we also know the exact parameters. So here you would see how these class conditional distributions would look like. So maybe we know exactly that for males we have a Gaussian distribution centered around 180 centimeters with a standard deviation of 4, and for women there would be an average of 70 centimeters with the same standard deviation of 4. So actually, sorry, I guess that's not standard deviation, but variance here. So standard deviation is I guess 2 for both of these distributions. So I think these distributions here are not super realistic. I guess I looked this up a little bit on Google. I think women are on average actually a little bit smaller. I think for men it's somewhat realistic, might be 179 or something like that. I think for women it was actually 166 or something like that. So these numbers are somewhat made up. I'm also assuming here that the prior probabilities are potentially the same. I guess that's not very unrealistic, but I will vary that also in the upcoming slides. And we could now talk about where the optimal separation would be between these two classes. Well, and that's exactly at the point where the two probability densities would intersect, right? So because for this region here, the class conditional distribution of the males is above. So this red density here is above, this black density is above the red one. So for every observation of centimeters, being in class male is more likely than being in class female. If this observation of centimeters is larger than 175, and the opposite happens here on the left-hand side. We can now also go through a simple computation, a simple application of Bayes' theorem to, for example, compute the posterior probability that for a person being male, given that we know that this person is actually 172 centimeters tall. So the idea is to look at this position here. This is the observed height. We can now compute the class conditional density values of x, given that we are a male or a female, and we can now plug these into Bayes' theorem as we've discussed before. So one thing I'll do here on this slide in order to simplify calculations is to assume equal class sizes. So I'll assume that my prior probabilities pi1 and pi2, or pi men and pi woman, are the same. So they are both assumed to be 0.5, so 50%. And I'll now, as explained before, compute this posterior probability here for y being a male based on our feature vector, which just contains a single entry. So the height being 172, and we'll compute that by applying Bayes' theorem. And that's, in that case, all of the pi k values, they cancel out because they're all the same. And we get simply here that we should take this value, so the density value, given that we are in class male, divided by the sum of these two density values. So we take that guy and that guy. So the probability here is this thing set into relation to the sum of these two, right? Did that here for the exact numbers, and the result would be that the posterior probability is about 13%, which means it's about 87% posterior probability to be female with such a height. And like I said, the computation is off because I'm using somewhat made up numbers here. You can do the same computation for unequal class sizes now with prior probabilities here for male and female. And you can then see that if you plot this, of course, the Gaussian distributions look a little bit less similar because they're here multiplied by the prior probabilities. Yeah, but similar, slightly more complicated computation allows us to compute here these posterior probabilities. So I guess I will not read that out. There are a couple of examples here in the slides which you can nicely follow along with pen and paper, but I guess it's somewhat boring if I read that out during the video. LDA is, as obviously in the name, a linear classifier, and that happens exactly because of this equal covariance structure in all classes, and because also of the assumption of normality, and that means that all of the decision boundaries here between the classes that the classifier produces, they're all going to be hyperplanes. It's shown here for the iris data set. I think when Fisher collected the iris data set and published that, I think he specifically did that to study things like LDA and QDA. We can again quite easily show this. So let's do this. Let's go through a little bit of math to actually prove that what I just explained, that LDR is indeed a linear classifier, is true. So on this slide, there's not a lot of new stuff. So we look at our pi k here. We'll use Bayes' theorem to turn this around. And in the denominator, we'll use the law of total probability to just write it in terms of pi k and these class conditional distributions. So for so boring because we already discussed that a couple of times now. The next thing we'll figure out is that this denominator here, this thing is just a normalizing constant. It is the same for all classes. So for all of these pi k functions, this thing here is completely the same. So we can just disregard that, multiply through with it, and not care about it anymore. So what we are now supposed to do is to show that this thing here is a linear function in X, potentially after some monotone transformation. And this is exactly what we're going to do now. So let's start with this guy. So pi k times the conditional, given that we are in class K. So the first thing I'll do, I'll not read out all of these terms because this is potentially annoying for you and also for me. But I'll explain how this works step by step so you can easily follow along or even do this yourself. So the first thing I'll do is I'll simply insert the definition of a multivariate Gaussian into this guy here. I'll already simplify this a little bit. I'll comment on that a little bit later, but I'll leave out multiplicative constants and I'll make that visible through that proportionality sign here. So I'll just insert, I don't know, I'll just insert the Gaussian density without of the first multiplicative constant in its definition. The next thing I'll do is I'll take a look at these terms a little bit. and separate them a little bit to make this a little bit easier to deal with. So there are terms in there which contain two axes. So these are quadratic forms in X. I've marked them here in blue. And then there are terms which simply contain one x, and I've marked this here in pink or something like that. And then there are terms which contain no x at all, so these are constant, and they are marked in orange. Now we can simply separate this a little bit, write down two exponential functions here, one of the blue guy and one for all of the rest. And I've also taken the liberty of pushing pi k inside of that x function, so I'll just put a log in front of it. Now, the next thing I can do is I can see that in this first exp, there is stuff that's constant, that doesn't contain any x, so I'll just give it a short abbreviation. I'll call that W0. And then there is this thing here, which is linear in X. So I'll say that that's X transposed times some vector WK. And then there's the rest, which I just copied over. And the last thing I'll do is that I'll look at this quadratic thing, which is bothering me a little bit because I want to enter with a linear term. But we are comparing all of these functions for all of these classes, so all of these pi k functions, and we're going to compare them, and figure out when they are equal. Now, this bluish term here is the same for all of the pi k's, right? There's no k index going on there. Why? Because this sigma here, the covariance matrix, right? We assumed not to be dependent on the class K we are in. That is the same for all of the classes, right? And that's exactly why the following is now happening, that this here is the same for all of our G classes, so we can simply remove this as well. So the only thing that remains is this thing here, x of something linear, and I said up to monotone transformations, if we can write the scoring functions as something linear in X, then we are good. Then it's a linear classifier, and this is exactly what happens here. You can also see here the exact definitions of W0k and WK. I guess that should have been now obvious from my previous explanations. If you want to, you can do a careful check that what I just explained is correct, because it was a little bit lax here by using these proportionality signs. I didn't want to write down too much and I wanted to be a little bit lazy. But actually, this still holds under careful checking. So fortunately for me, so the major thing I did is that I left out positive multiplicative constants. And the other thing is that this thing here is same for all of the classes, but I can obviously still do that, right? First of all, when I compare the classes, I can just like divide through by that term, or I can simply say that if I don't do log at the end, but I do a transformation like that, so log of, I don't know, some multiplicative constant times my argument plus b, that this is still a isotonic transformation, especially if my a is positive. So all of that still works, and we are fine with that, and we can actually, what we actually did is fine and correct. Okay, here's the definition of quadratic discriminant analysis. I guess we can maybe go through this a little bit faster now, because this is a very, very simple and straightforward generalization of LDA. So again, we assume that our class conditional distribution is a multivariate Gaussian, and the only thing we'll now do is we'll relax our assumption that the covariance structures are all the same. So they can now be different. So just give them individual symbols, sigma k, and because of that, you can also see here that they have different contour lines here. Now, when I plot and visualize these things, here is the continued univariate example. So if I just have one feature, I'm now allowing that the variances here, class conditional variances, are not the same anymore. So they're not 4. So I'll have now 2 made up numbers here. So for women, it's supposed to be 4, and for men, it's supposed to be 9. No real good reason for that. Just wanted to continue this simple example here. And this now actually leads to the following classification rule. So we would actually say that if we are inside of this interval here, so this is the region where the red class conditional density is above the black one. In this interval, we would classify everybody to be female, and outside of that interval, we would classify everybody as male. So it really makes no sense, but this is what would happen here. And just wanted to show this, continue the example. In this case, we would have constructed something which we would call a quadratic decision boundary, which in this 1D case weirdly is an interval, okay? This doesn't make sense if you write down formulas, so maybe do this. So you would have something now like x minus some value alpha squared. You're checking whether this is larger than some value beta, and if you do this just for one number, you'll figure out that this is basically an interval, okay? Makes a lot more sense to visualize this in 2D, which I did here again on the iris data set. So maybe let's start with that. So that would be QDA applied to the iris data set, and you can now see way more nicely these quadratic decision boundaries between classes. You can also write this down algebraically. I'll do this now way faster. So we start again with this prior times the class conditional. We plug in our definition of the multivariate Gaussian, leave out the normalizing constants, the multiplicative constants, and basically we don't have to do anything now. We just take the log of this thing because the inner part of this is already a quadratic form in X. So we take the log to get rid of the X, and then we look at this and we can immediately see without any further transformations, except for the log, that this is a quadratic form in X. Okay, so also even easier than in LDA, where we had to do a little bit of work. I guess we should also talk about how to concretely construct the model, how the parameters are estimated. This is also fairly simple, because the only thing we now have to do is to estimate the parameters for the class conditional Gaussians. So I don't know, we have these class conditional Gaussians here, and in order to represent these multivariate Gaussians, so per class, we need to estimate a mean vector mu, and we need to estimate a covariance matrix sigma k. So maybe let's actually even start with QDA, because that's even simpler. So for each class, you now take the data that you've observed, you compute the average vector across all observations, so the average feature vector, and that's your mu k. And for your covariance matrix, you also apply the estimation formula for a covariance matrix in absolutely the standard manner. That's it. I guess you also need the prior probabilities. So these pi k guys here, so you just count class frequencies. That's it. For LDA, you do exactly the same for the mu vectors. Just estimate the average vectors. And for the sigma to be the same across all classes, you do here the normal estimation per class, but then you average everything across all classes. So you also call that the estimation of a pooled covariance matrix. Yeah, but it's just like doing that per class and then averaging across the classes. I guess we can talk a little bit about number of parameters in these two models. So most important part is this estimation here of the covariance matrices. So these are P times P matrices, right? Because we have P features. So if we estimate this for QDA, how many parameters do we have? We have P over 2, which is P times P plus 1 divided by 2. Why is it not P squared? Well, covariance matrices are, by construction and definition, symmetric. So we just have our parameters here in this part. So this is why this is P over 2. And for QDA, it's P over 2 times G, because we have to estimate such a covariance matrix for each and every class. So that's actually quite a lot if P is large. So if this is 100 or 1,000, this can be actually, can obviously become quite large because it is quadratic in P. So for LDA, it's a little bit less because we only have to do this for one class. And depending on how many observations we have, so how large our sample size is, that actually matters. And I'll show this in an example in a few seconds. Actually, we'll do this very soon because on this slide here, there's a short pen and paper, so to speak, calculation of how to estimate the parameters for QDA. I really don't want to read this out because this is really, really simple. So I guess we can look at it for a few seconds. But if you still feel unsure how to do this, grab pen and paper and just do this calculation yourself. It is really simple. So here we have a two-dimensional data set. We have maybe only 2 observations in class 1 here, and we have 3 observations in the other class here. We calculate our class priors, 40% versus 60%. Calculate our mean vectors by averaging this, and the other mean vector by averaging this here. And then finally, and I really don't want to read that out, just do these calculations here for the estimation of the covariance matrix in the standard way, and we are done. Okay, maybe a little bit more interesting, especially for practical applications, is this simple and final simulation study here. So I wanted to benchmark the methods on a very simple toy data set. Actually, it's multiple data sets because I'm creating them in multiple dimensions. So the data here is really normally distributed. So I'm not violating the assumptions of these 2 techniques. So it's normally distributed per class, but it's unequal covariance matrices per class. It's 2 classes here. So it's like a mean vector here, a mean vector here, and then something like that, and I don't know, something like this, okay? So that's actually the assumption of QDA, right? Conditional, normal distributions per class, but unequal covariance structure. And I'll now sample from this in multiple dimensions. So I'll do this in 2 dimensions, 5, 50, 100, 200, up to 400. And I'll construct an LDA model and a QDA model, and I'll cross-validate both, and then figure out how well they work and compare them. And I guess at first glance, the assumption would be that QDA should always be better here, right? Because the assumptions match QDA, or the data generating process, the construction of the data generating process matches the assumptions of QDA, but not of LDA. But is that actually something slightly different happens, right? So in lower dimensions, this is indeed true, right? So up to dimensionality of 200, QDA is really better. So nearly has an error of 0 here. So maybe something that I should also say is that I didn't really took care in the construction of this example that the base error for the DGP is the same when I vary the number of dimensions. I could have done that. I guess I was a little bit lazy here. But the idea is that in every dimension, the assumptions match QDA. And if we could estimate our QDA model perfectly, which we cannot because we're using a finite amount of data, then QDA would actually always be better, okay? Which should not happen is this kind of situation where after a certain dimensionality here, QDA degrades and LDA becomes now quite a bit better. Or, well, actually, if you know these things a little bit, it is not too surprising, because what happens here is that although the assumptions of QDA match the underlying distribution much better, what screws us here is that we have a way larger amount of parameters to estimate, and this reduces the performance of the model considerably if we're working on these finite data sets. And in the end, although the assumptions of LDA are violated, makes the model perform better in these higher dimensions. And this is something you can see quite a couple of times if you compare these methods on real world data. And we'll see a similar situation in the upcoming session where I will introduce the naive Bayes model. Okay, this ends it here. See you in the next session.